This is my university, and we are located approximately here outside of Copenhagen. And the reason that I'm not here in person today is not the COVID and travel restrictions, but it's due to my daughter here who just graduated from high school. And I wanted to show this picture because this is like the first and last time in Denmark that you get a hat when you graduate. So yeah, let's get to the technical part here. Okay, so I want to talk about compressed tries, and please everyone, both online and offline, interrupt if you have a question. I won't see your hands, but just unmute and talk. So I'm going to talk about string dictionaries. So in the string dictionary problem, we have a set of strings. And what we want to do is to do a prefix query. So we want to ask if some pattern P that we are giving at query time is a prefix of one of the strings in our set. And the standard solution for this, as I presume that most of you know, is a try, right? So we just have a try here, and it spells out all the words in our dictionary. So we have BA and BBB and CAA, BA, and so on. And using a try, a standard try that takes up order of n space, where n is the total length of all our strings. So, oops, back here. So n is the total length of all our strings, and PM is the length of our pattern P. So we can just, in constant time, we start in the root and then we just walk down. If we want to search for CAAB, for example, we start up here, we walk down, find C, find an A and a B, and then we know that it's a prefix of one of the strings. Sorry about that. Yeah, just had a call coming in. I haven't tried that before. Okay. So this is the standard way to do it, and we can do this in the standard word-RAM model, where we can use hashing, for example, to figure out which edge we should follow out of each node. So what I want to talk about today is, can we do this better? So what if the strings shares a lot of things? What if this try here has a special structure? Can we save it in smaller space and still get a nice query time? Okay, so Benoit et al. And Ramen et al. Has solved this in the word-RAM model, where they use n divided by log sigma n space and order of m time. This is also called a succinct data structure, and Rashid will talk about that on Friday, I think. Not this specific problem, but about succinct data structures. What I will talk about today is, what if we want to study this problem in the more restricted pointer machine model? So all these techniques to get these results here in the word-RAM model, they rely heavily on tabulation, direct addressing, word-level parallelism, hashing, etc. So what if we go to the pointer machine model, where we have none of that? And we will see that we can get almost the same bounds. We'll get a little larger query time. So in the pointer machine model, every data structure can be viewed as a directed graph with a bounded out degree. So every node contains a constant number of data fields, and it can also contain some pointers to other nodes. And then to access the data structure, you have to traverse the graph from the root. And you all know data structures like lists, like linked lists, search trees, and so on. So in this model, it is not, we cannot do random access. We cannot say, give me the 5th position in the list, or we cannot do hashing and stuff like that. So that's the model we are going to work with. Okay. Any questions at this point? Okay, so the plan is that, well, I will talk about how we can solve this compressed string dictionary problem in the pointer machine model. First, I will talk about DAG compression and top tree compression of tries. So these are ways to compress trees in general, and specifically also tries. Then I will talk about how to search in the compressed try. And on the way, I will show a data structure for part extraction in an edge-labeled compressed tree, and a data structure for weighted level ancestor in a weighted tree. And both of these things, of course, also in the pointer machine model. Okay. So when we want to compress trees, the goal is to identify repeated patterns in the tree and compress them. And when we talk about DAG compression, what we do is that we find equal subtrees where it's the full subtree that is equal. So this whole subtree here and this whole subtree here, you can see they are equal. So instead of saving the whole tree and saving both of them, we can make a pointer here over here instead. Okay, so we can compress it like this. But besides that, there's not a lot more to do in this tree. The only thing we can do is to merge all the leaves together. So a DAG compressed version of this tree will look like this. And you can see now we can do exactly the same navigational properties. We can still search down from here and search for C, A, and B, and see that this is a prefix of one of the strings we have saved. But this is a kind of restricted model. Let's say that we have a file that looks like this, for example. I'm just putting on some letters here. Then using DAG compression, we can really not compress this at all, except for merging all the leaves. So this is what we will try to fix now. So to do that, we look at top tree compression.
Mais à Aubagne, les policiers municipaux sont équipés sur leur gilet de caméras qui enregistrent toutes leurs interventions. Les images permettront peut-être plus tard d'identifier les motards qui ont pris la fuite.
Inge, I apologize about that. Can you unmute yourself again? I'm sorry. Somebody came on with the microphone. I apologize.
Okay, that's fine. Yes, I'm.
Thank you very much. I apologize.
Oh, that's fine. At first, I thought she was saying something to me, but okay. So I want to tell you about top tree compression, which is basically actually a transformation of the tree that we do first. So we do a transformation of the tree, a kind of a clustering, and when we have done that, then we can show that the DAG compression will always compress the tree. Okay, so it's yeah. So what the DAG compression could do was to recognize fully repeated subtrees, right? Where it was the full subtree that was equal, like this and this here, for example. So what we want to do now is try to also identify internal repeated patterns like this one. So here we have a root node here with an A and a B, and the root node has an edge out, and this one also has some edges out. So this one has connections to other and this one, but nothing else. And that's exactly what we have also here, a left child with an A and a right child with a B, and a node here with connections to others and a node here with connections to others. So we want to recognize these kind of patterns also and be able to save them using little information. So not save them all the time they occur in this tree. You can actually see that this specific pattern occurs also here and here. Okay, so we want to identify internal repeated patterns, and of course also still these ones that we could with the DAG compression. So what we are going to do is that we're going to build a clustering on the tree, a hierarchical clustering, and from this clustering that will give us a new tree, and then we're going to compress that tree instead. So we will do this by merging edges in the tree. So we will merge them 2 and 2, level by level. So first we write up all the edges down here. So you can see they come in order here, almost at least, B, A, B, and so on. So these are the labels on all the edges. And then we have a number of different merges that we are allowed to do. So one merge of type 1 is this kind of thing. So that requires that we have an edge that then down to a node that has only one child, and then an edge more, and then these two boundary nodes here, the solid ones, can have connections to other nodes. Okay, so we have such a pattern here, for example, where only these two have connections to other nodes, or here, or here. Or actually, only this one was of type 1, because only in this one, the bottom node had connections to others. The two other ones, this one and this one, is a type 2 thing, merge that we could do. And then we also, so these we call vertical merges. We also have some horizontal merges where we can take a little pattern like this. That would be a type 4 merge, where this node here and this node here has connections outside, but this one does not. Okay.
Can you say again what signifies the what is signified by a solid dot, an open dot, and no dot at all?
Yes. Okay. So if we take the blue one up here, for example, type 1, then this is a type 1, and this would be solid, and this one, and that means that these nodes here we call those boundary nodes, and they can have connections outside, or have connections outside, whereas the not solid node here it just shows that there is a node in the middle, actually, down here, that they have in common, right? So more precisely, we could draw it like this. Does that make sense?
And what about in number 2, where the bottom doesn't have a dot at all?
Yeah, that would happen in this case. So it's actually, it should have had, that's a good point. We didn't do that in the paper, so I don't know why we did this for many years. It should have another one, but later it can look different. But yes, it should have had a dot also.
Okay, thanks.
You're right, and also these ones should have, but just not solid ones. Yeah, thank you. So let me just actually keep that here. Then we have an edge here and here, and here and here, and we have a node here, and we also do have a node here, right? And a node here, like this. Okay, and we are going to do this in a specific order, and I'm not getting into that too much into that specific order, but that's important for showing the compression ratio. But if you just want to build it, I mean, you could do it in any order, but if you want to prove that this always gives a compression, you have to do it in a specific order. So we are going to do the horizontal merges first. So we'll find a cluster here. And then we'll find the two nodes corresponding to that down here. Oops. So there'll be this one, and we'll give them a parent. And we'll write a 4 because it's a type 4 merge. And then we do that again. We find another one here. It's also a type 4. We find the corresponding nodes. So the nodes leaves here in the top tree that is going to correspond to these edges. And we give them a parent, label 4. And the same thing here. Also get a type 4. And then this one finally, that will be a type 5, because none of these two nodes here have any connections outside. So this is a type 5. And the last one, the last horizontal merge we can make is this one over here. Okay, and now we cannot do any more horizontal merges. So we cannot use the same edge twice in one round. And this, for example, would not be legal, as there would be 3 boundary nodes having connections outside, and we allow only 2 boundary nodes. Okay, so first we do the horizontal, and then we do a vertical merge like this. There's one here, and that is a type 1. So we find the nodes and we put a 1 here. Okay. So is this first one clear what is happening? Then what we do next is that we merge, so we contract these edges. So we are going to, instead of these 2 edges here, we'll put a new edge from here to here, and we'll put a 1 because a label with 1 because it was a type 1 thing. Over here, we will delete this one and just keep this, and it will get a new label with 4 instead of a B. And the same happens here. We're deleting this here. We're deleting this one and getting a 4, and so on. So after we've done this, the tree looks like this. Okay. So now we have a new tree, and we can do the same thing again. So again, we start by trying to find horizontal mergers. We find one here, and that is a type 3 because the boundary node is to the left. So we find the corresponding nodes in our tree that we are building down here. And we see that it's, let's see, where is it? It's this one and this one here. So we make a parent to these two that is labeled 3. And it's very important here that we always put in the horizontal merges, the left child is also corresponding to the left child here and the right child to the right. And in the vertical merges, we will always put the top to the left and then the bottom to the right. So this is the only horizontal merge, and now we can do a bunch of vertical merges here. So we get this one, the 4 and the B. So that was this part here. We can do this one and this one. And they'll give us a new node here. So now we have a new layer of nodes up here that we can merge together with, all the roots in these small trees are the ones that can get merged in the next level. So again, we are going to replace these 2 edges by one new edge. And here we'll delete this one and give this a new label. So these clusters grow larger and larger, and we keep continuing doing this. And now I'm just gonna rebuild this tree so it's easier to draw the clusters, but it's the same tree that we continue with. So now again, this time we can only do vertical clusters. We can make 3, and they were all of type 2 because they had no boundary nodes in the bottom. So that gave us these nodes here. And we merge the edges and get a new tree. And I'm just moving it a little around so it's easier to work with. Now we can do, finally we can do some horizontal merges again. So we go like this and this. Get 2 new nodes. The first one was a type 4, the next one of type 3, this one. And now we see we only have a part left. Just gonna stretch it out like this. And now we can do one vertical merge of type 2. So that gives us this new node. And then finally, in the last round, we also do a type 2 merge. Okay. So this gave us what we call a top tree.
One question.
Yes.
Anything in this procedure that requires that the tree is binary?
No, the tree that we built will be binary, but not the tree we started from.
So when this type 3, type 4, and type 5 mergers,
yes,
this gives the impression like you are talking about left and right, and like
okay. So what I do,
okay.
Let me say. So let's say I had just a small part of the tree like this, right? Then I could do a merge here, only taking 2 of them, right?
Okay.
So I can take 2 of them but they have to be next to each other. I cannot take this one together with this one or something. I can take 2 continuous.
Okay.
Neighbors.
Now it's clear. Thank you. Thank you very much.
Thank you. Yes.
Okay, excuse me.
Yes.
Yes, I have another question here. Is this process unique, or do you make some choices? For example, in the last step, when you had only, I think 3 edges left, you made type 2 to merge of the 3 bottom ones? Could you
Yes.
instead have merged the top ones?
I could. There's a very specific order you will have to follow if you want the worst case guarantee that it always compresses in the end in a minute. But I mean, the top 3 transformation, basically you could do that anyway. That was, I think,
Okay, but
most ways where you are consistent, you will get a consistent result that will compress well.
Okay, so if you have some choice, you have some fixed order that you follow. Okay, fine,
Yes.
thank you.
Okay, so this gives us a new tree, and of course this doesn't take any less space than the other tree we had before, right? Because now we have the number of nodes in this new top tree, as we call it, is actually 2 times the number of edges in the original tree, right? So what is the point? Well, let's look at it. So here we had the original tree, and here we have the top tree. And recall that I would like to find these internal patterns also in my top tree, right? So now some of these internal patterns will actually correspond to full subtrees down here in my full subtrees in my top tree. Okay, so this part here is exactly this little part here, and this part here is found down here, corresponds to this. And we also have that these 2 here still corresponds to full subtrees. That will always be true. So the point is that we can now prove that we will get a certain amount of these internal trees also. So now when we do a DAG compression on this, these will all turn into the same small subtree, okay? So it's not very pretty, but when we draw the DAG, it'll end up looking like this. So you can see that this subtree here with a 4 and an A and a B, it actually has 3 pointers, 3 parents here pointing to it. That corresponds to this one, and then this one over here, and not this one because these 2 are already merged by this 2 here pointing to this 2. Okay, so that's this one pointing there instead of pointing down here. So now we can compress the top tree using the DAG compression. So why use this top tree compression thing? Well, the point is it's optimal in the sense that we can show that it will always give you a tree of size order of n log base sigma of n, where sigma is the size of the alphabet. Okay, oh, not times, it should be divided by, let me try that again. N divided by log sigma n, okay? So if the tree is large enough, we will compress it. So the top tree compression scheme was invented in 2013, and then in 2018, Dodek and Gawitowski showed that you can get optimal in the original paper. There was some fraction here. Okay. It's quite simple, and it's basically just this nice transformation, and you can also use this top tree clustering. It was originally used in graphs in general to support the dynamic graph operations. I think it was invented by Alstrup et al. Back in the 90s, something. Okay. So using the top tree, it is also easy if you want to know what is the label of a certain edge, for example. It's easy if you put on some numbers up here. You can see, then you can, if you know what the size of a subtree is and you want the 15th label in pre-order, then you can just say, okay, should I go left and right depending on the size of the subtrees below? And when I say subtree, I mean if you like look at the tree that this subDAG actually spans. Okay, so then you can just follow a path down to find the correct edge, find the label down here, and that will take order of log n time, because the top tree, that's another property of the top tree, that it always has high order of log n. So it's very easy to use for navigation if you want to know what is at a specific position, either value in a node or on an edge. Of course, that's not what we want to do in tries, but let me just take another thing first. So this can be much better than DAG compression. Let's take this example we had before that I showed with this caterpillar graph or try here, where the DAG compression cannot really compress it at all. What happens if we use top tree compression here? Well, in the first round, we would make a lot of horizontal clusters like this. And we would build a new layer here. So we would halve the number of nodes already in the first layer. In the next round, now this is just a path. If we contract all these edges, that means we would delete all these edges out here. So now we just have a path. So now we can do a number of vertical merges, and we can again halve the size of the path. Okay, so now we can do 4 vertical merges. So the top tree looks like this. Next round, well, now this is an edge, this, and this. So again, we can do 2 horizontal merge or vertical merges now. And then in the end, we'll do 1, and this will be our top tree. And this top tree, as you can see, is very DAG compressible, because basically all parts from one level are the same down to a leaf. So the space now for this tree here is just 2 times log n, where n was the length of this part here. Yes, so it can be exponentially better than when you compress with the DAG compression. And there's also cases where it can be a log factor worse. So sometimes it's better to just directly use the DAG. But it's only a logarithmic factor as it can be exponentially better than the DAG compression. But back to the try problem. So are there any questions for the top tree compression before I start to talk about how we can search in this?
Yes, there is a question. Could you come?
Yeah.
Can I just speak?
You can just speak loudly.
So like for the listing of the alphabets down at the bottom, I think the first example was doing depth research.
I can't really hear you.
Yes, please come in.
Yeah.
Move the speaker.
Yeah, we can move the speaker, but it doesn't have a very long wire. I'm sorry. It may has a very quiet voice.
I tried to raise my voice.
Yeah.
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 I was asking like, so for the first example you did, the alphabet you listed at the bottom looks like depth first search, and this one looks like breadth first search. So is there a specific order you should follow?
Say again, so what looked like a breadth first, a depth first search?
Sorry. I said for the example you did earlier.
Yes.
It looks like a depth first search for the alphabet you listed at the bottom. And this one looks like a breadth first search.
Ah, yeah,
Yeah,
okay.
so-
Basically, I just laid it out such that that there's no order you should follow. I mean, it will always be a tree. I just cheated and laid it out such that the tree actually looks nice and can be embedded without any crossings.
Okay. Thank you.
Does that make sense? I mean, it will always be a tree. You don't have to lay it out from the beginning. You just need to merge the nodes and give them parents. And you're right here. If I had put them in pre-order here, but I would have had depth first search. I would have had all the A's, and the tree would have been ugly.
Oh, I see. Yeah, I was just thinking like the earlier one looks like a depth first, and this one looks like
Yeah, and the earlier one, it wasn't precisely the pre-order because there I also cheated, because otherwise it wouldn't have been pretty either. But it doesn't make sense.
Yep. Thank you.
Yeah, good question. Yes. Other questions?
No, not at the moment. Thank you.
Okay, good. Okay, so now the thing is, we want to figure out how to search in this, right? So we want to just use this this top DAG here. The other two are actually not there anymore. We are only saving the DAG. So what do we do? Now we want to stand at the top here, and we want to search for our pattern, CAAB, for example. And we need somehow to figure out, how do we do this? How can we augment this top DAG in a way so we can actually also search? And recall that all these nodes here in the top DAG, they correspond to one of these types of merges here, right? So I'm just going to color them. So all the blue ones are the vertical merges, and all the red ones are the horizontal ones. And we are going to treat those differently. So let me start with the easy case, which is the horizontal one. So if we have a horizontal cluster, it came from one of these three kind of merges. So if we look at it on a higher level, I mean, on the lower level, of course, it's like, I mean, we made it using one edge and another edge here, and at the point where we made the merge, right? But earlier we had already merged a lot of things to get these two clusters. So actually, this whole cluster here is some connected subtree of the original tree, and so is the other one. So that is, by the way, always true. If we go back here, we see that any sub-DAG here or subtree of the top tree corresponds to a connected subtree up here, not necessarily a full subtree, but if you take everything that a node spans over here, then that is going to be a connected subtree in the original tree. Okay. So if we look at it at a higher level, well, could be a lot of edges actually going out from this node here, and we want to figure out, should we recurse on the left-hand side or the right-hand side? Let's just call that A and B. So the cluster we are looking at merged these two, so let's call that cluster C, and now we want to figure out, should we go down this cluster or this cluster? So the horizontals are actually quite easy, because what we can do is just store the label of the edge to the rightmost child of the top boundary node in A. So A was the leftmost cluster here that we merged. So the rightmost child in here is this one. So if there was a D here, for example, we will, together with C, store the information that this had labeled D. So now when we come and search, we compare to the next letter that we want to compare it in our pattern. And if that letter is after D in the alphabet, we go into the B cluster, and otherwise we go into A. So that way we can, every time we stand in a horizontal cluster, figure out which way to go. Okay, and then there'll be new clusters. A is composed of smaller clusters, and then we again have to repeat this. Okay. Now the problem is a vertical cluster. Because if we have a vertical cluster, now we would like to quickly know, should we recurse in A or should we recurse in B? And if we had the word ramp model, well, we could cheat, and then we could save a hash for the for the whole word you would have if you looked at all the characters down here on this spine part, as we call it, from this boundary node to this boundary node, and we could just compare that in constant time. But we don't have hashing or any stuff like this, so we will have to find a way to compare, to find this way here and figure out, if we look at this whole part from the top and down here, where do we fall off? How long can we follow this matching our pattern? Because if we fall off the spine part up here, we need to recurse in A. If we can reach all the way down to this, then we can recurse on B. Okay, so we want to figure out, where do we fall off? And we want to do this quickly. We could use, as I said before, you can say, okay, this is this number edge, so I can just look it up using this random access where I walk down in the tree and figure out what is the label of this edge. But that would cost me log-in time for every edge I want the label of, and I want to do it faster. So I want to do what I call a spine extraction. So I want to return the characters of the spine online from top to bottom. And actually I want to do it in this A cluster here and figure out, can I reach all the way or will I fall off somewhere in here? And when I say online, it means that I need to get the characters one by one from the top, and I can stop at any point and not use any more time. So I don't want to use time proportional to the length of the path, but only proportional to the length of the path that I actually traverse. So this turns out to be quite a lot more complicated. So what we will have to do is that, okay, we look at our top DAG, and then we construct what we call a vertical top DAG. So we throw out all the red nodes, all the horizontal merges, clusters, and only keep the blue ones, so only the horizontal ones. And then depending on what kind of node it is, we'll have to figure out where it should point, okay? So we only have the vertical clusters, and which edges do we have? Well, if we have a type 1 thing here, then it should have both a left and a right child, because it has both a spine up here and a spine down here, and we want to be able to follow both of these. So of type 1, it will have its left descendant should be the cluster, the vertical cluster corresponding to this spine part, and its right child should be the vertical cluster or leaf corresponding to the spine part in the bottom part here. So if we look at this node, well, the left part, that is already a vertical cluster, so it can just point directly to that. That will be the spine of the top part. But here we get a horizontal cluster that was of type 4. So that means that the spine goes on in the right child of this 4, so we go down to B, and therefore we also point to B here. Okay. The type 2 clusters, in those we are only interested in the spine part up here. There's not really a notion of a spine part in the bottom part, so it's only in the top part. So they just point to the single vertical descendant or leaf whose spine part is A. So if we look at the top node, it should be its left child. So we go here, that's a horizontal merge. It's a type 4, so we should follow the right child, and we point down to C. Whereas if we take this one here, corresponds to this, we should take the left child, it goes directly down here, and so on. Okay, so we built this new top DAG, and then we want to only traverse this one, and we want to do that fast. So that's the main point. Okay. And again, just notice that, so this node here corresponded to a node or cluster in the whole top tree. And if we look at everything that spans, that corresponded to a subtree in our trie. And if we go down here and look in the vertical top DAG, then it corresponds exactly, these leaves here corresponds exactly to the spine part up here in the top part of this cluster here. Okay, and they come in order, it says A, A, B, so they come in order from left to right. So what we do then is that that we do a kind of just a depth first search actually in this thing here to find these nodes, and that might seem that that could take too long time because we might have to follow a long path down, and then we go up again, and then maybe we read a lot of nodes, and then we're done just after reading one letter here or two. So we do a little more. So we store the first label on the spine part in each cluster. So if we only read one, we don't have to walk down. And then we walk down, and then we want to find the cluster to exit from. So if we walk down here, and let's say we read A, and then we fail, so then we want to exit from this cluster. We want to continue our search in the original top DAG from this one here. So what we show is that the time we use to do this depth first search is no more than the depth of this whole cluster minus the depth of the node where we exit. And since in the end, when we walk down, we'll figure out where to get out of a blue cluster, and then we need to continue down into some red cluster. So we always, after we figured out which cluster we should get out of, we always walk down in the original top DAG. So all in all, we show that this accumulates to just being log n. And I don't want to go into this because I see I'm using more time than I thought I would, and I want to show you something that is more interesting and probably a little less complicated without having read the paper. But all in all, what we get here is that we can get this n divided by log sigma n space and order of m plus log n time. So we show that all the time we use on traversing down here and doing depth first traversals over here, in total that takes no more than the length of our pattern plus the depth of this top DAG here, which is log n. Okay. So that is one result. We also show another result where you can see that we can also get m times log sigma n, which might be faster depending on, this is at base 2. So depending on, on things, this might be faster, okay? That other solution needs quite a lot of techniques, but there's two, it needs a new technique both for the vertical and the horizontal clusters. And what we show is a way to get path extraction. I'll get back to that in a moment, a very elegant, easy solution for that, and how to get weighted level ancestor in trees in the pointer machine model. So I want to get to that. So path extraction. So now we're just back to, just imagine you have a tree and you want to do the following query. You want to come with a node V, and now you want to report the nodes from the top down towards V, and you want to be able to stop at any time, any point in time. So that's again what online means. And we want the time to be proportional to the number of nodes that we meet on the way. So we actually want constant time per node. Okay. So again, in the, it's very important that we can stop at any time. So I start in, it's on the path down to V, but I might stop after 3 nodes. If I always wanted the whole path, I could just walk up following parent pointers, right? But now I want to walk down and I don't know in which direction to go towards V. So that's the point. In the VertRAM model, you could use a level ancestor data structure that in constant time allows you to jump up to any ancestor. So you say, give me the 7th ancestor, and then you can just jump up to that, and you could just jump 1 less every time in constant time. In the pointer machine model, you could also use a fully persistent linked list or queue. We show another solution that I think is quite elegant and very simple and has some nice tricks in it. So here's the point. So we have our tree. This is a general tree. And then we divide the nodes into a top and a bottom. And all the nodes that are in the top tree up here are all those whose depth is less than the height. Okay. So the path to the node from the root is shorter than the path from the node to its furthest away leaf. Okay, so those are the ones that are in the top, those that have less depth than height. Now look at all the nodes that are leaves in this top tree up here. We call this the there's another top tree, but it has nothing to do with the other top tree. So in the top just, okay? So all the leaves in the top, for each of those, we actually store the whole path down to it. So we store in a linked list, we store the whole path down to it from top to bottom. And we do that for every node here. And that seems that should take up a lot of space. But let's look at it. So it's, what is it? Well, it's going to be the depth of U for all U that are a leaf. Okay, this is not very pretty. Where U is a leaf in the top. Well, we know from the definition that this is less than or equal to the height of u for all u's that are in the top, right? And if we look at the height, that means that they all have some long part here down to the furthest away leaf. All these parts are disjoint. So the number of nodes down here must be at least the number of nodes we just saved up here. So these nodes will pay for this part. These nodes here will pay for this part. These ones will pay for this part, and so on. So we know that the height is more than the depth, and we know that all these parts down here are disjoint, and that means that the total sum of all these heights is no more than n. Okay, so the total space for saving all these parts for all these nodes here is no more than n. Okay. And so what we also save is for a node in here, we also save some descendant below it, just any descendant below it of these leaves, right? So every node in here will point down to a leaf, one of these leaves here. Okay. So in the top, we save a pointer to a leaf below for each node. And in the bottom, if you're a node in the bottom, you save a pointer to a leaf. It's not really a leaf, right? But to one of these nodes above you. There's going to be one unique node above you if you're a node down here. And then, so in total, this is going to be linear space. How do we do a query? Well, if you ask for a node in the top, you just go down to your leaf here, and you traverse the linked list you have saved from the beginning until you don't want to read anymore. So you just, that's easy. What if you're in the bottom here? Now you don't have a list. Well, you jump up to this node here and start reading this from the top. So this node has its whole part saved. So you read the first one. And while you do that, every time you take a step down here in this linked list for this node, then you go one up here and save this information. Okay, so when you have one down here, you go one up. Every time you go one down, you go one up, so on. And you will reach this from the bottom before you reach it from the top, right? Because all the nodes up here have depth less than the height. So that means once I have read everything down to here, if I want to read all that, then I have saved all the information on what the path down here is. So now I can stop at any point in time, and I've only used constant time per node that I read. Okay, so this gives us linear space and constant time. Questions for this? I think this is a cute little part extraction data structure. And we use that in to do the spine part extraction in the top deck. Then another problem we look at is the weighted ancestor problem. So now we have a weighted tree. So all edges have a label, an edge weight. So maybe it could be 1 and 3, 4, and so on. And then the weight of a node is the sum of the edge weights down to that node from the root. So this would be 8 and 13, so on. And now the weighted ancestor query is basically a predecessor query. So you want to find your deepest ancestor, such that that if you take the parent of that, then it's the weight of that node is more than the x you come with. So you come with a node u and a value, and then it's basically a predecessor query on this that you want on these numbers. And we show that this can be done again in linear space and in this time. So it's the logarithm of the depth of the node that you start in, and this is the weighted depth, divided by the depth of the node that you return, minus the depth of its parent. Okay. And this is interesting because you can get this to telescope if you want to use it for random access and other kind of things when you want to traverse the whole top deck. So that's why this part here is interesting. Okay. So here's another tree technique that we use often that I would like to show you. So we have our tree. And now what we do is that we partition it into slices. So in every slice you have all the nodes of a certain depth. So here you have those of depth 1, depth 1 and depth 2, depth 3 and 4, then 5 to 7, and so on. So if you look here, they have depth between 2 to the I-1 and 2 to the I. Okay. So for any node inside such a slice here, we will save a leaf. If we look at this slice here, it partitions the tree, right? It cuts the tree into pieces. And there's going to be some nodes here that do not have any descendants inside the slice. So this node is in the slice, but it doesn't have any descendants in the slice. So you will point down to such a descendant of it. So that's query U. And now, since we're doing level ancestor, that was, or not level ancestor, weighted ancestor, which was basically just a predecessor query on a path, that didn't depend on where we started. It only depended on the weights of these nodes here. Then it doesn't matter whether we start from U or from one of its descendants. So if we get a query now, we will never ask for U. We'll just say, okay, we'll go down and query from the node you pointed to down here instead. So we save that information so we can directly jump down, and now we only need to worry about leaves in these small subtrees that we got from this thing here. So now every such leaf will point to its highest ancestor inside the slice. Okay, so that would be this one. And now if I want to do a query on U, I go down to the node here, query U. I go up to W and I compare the weight of W and the weight of the parent of W to each other. And now there's several cases. So if the depth of the parent of W is greater than the X I'm looking for, then that means I need to go up higher. So I'll continue again, I'll start again, but now I'll just imagine that P of W, the parent of W, is the node that I started querying from. And since these slices are exponentially growing, we can only do this a logarithmic number of times. I could also be lucky that this one is smaller and this one is larger, which means I actually found my node, so I will return W. Or it could be that W actually is, the depth of W is smaller than X, and that means that my answer lies somewhere in here, in this tree, inside this slice. So then I have to figure out what to do in the slice. So as long as I'm either finding my final node here, or I'm continuing it up, or I have to solve it inside a slice. And whenever I jump up, I can only use that log the depth of U times. So to solve it inside such a tree, now we have a tree where the depth is less than or equal to 2 to the I for all the nodes in the tree. And we want this query time here that would give us what we wanted in the end. So now we can do yet another partitioning of the tree. So we take all the small trees we have in this slice, we take them and we look at what happens if you go into half, if you look at half the depth. So all the nodes that have depth less than 2 to the I-1 are up here, and all the other ones are in the bottom. Okay. And now we are only going to worry about how to check for nodes down in the bottom of a tree. So if we have such a new node U, it points to its highest ancestor in the bottom here, that is in the bottom. And it also points to, has a pointer, if you take the parent of that and then a leaf up here, and then it also points to a node down here that we call bottom U. So what is that? Well, we are going to recursively continue either in the top, and then we just take the whole tree in the top, or in the bottom tree here. But if we continue in the bottom, we first delete all the leaves. So bottom of U here is a leaf in this forest over here. It's this node here. So that's what we save. So now if we want to make a query on U and we want to find the deepest ancestor that has a certain weight, then what do we do? Well, first we go up and check the parent of check U and compare that to the depth of this one. And either we are lucky and this was actually the final edge we ended on, and we can return this. So if this is smaller and this is bigger, then we just return this node here. If this is bigger, that means that we have to continue further up. So then we continue from this node instead, because we always want to continue from a leaf. And then we do that over here. So we continue here recursively here. Otherwise, we compare to the parent of U and check whether U is actually the answer. If this is smaller and this is bigger than X, then we just return U. Otherwise, we continue over here with this node here, that is bottom of U. Oh. Like this. And we keep doing this recursively. Since we are deleting all the bottom nodes, all the leaves over here, and it's only the leaves that are saving, only leaves over here are saving information, and they are not there in the recursive part. We only use linear space because we only save a constant information for every node in the tree. And then using recursion and doing the calculations, we get this. So I think this is a quite complicated but very nice recursive structure to show that we can get fast weighted ancestor even in the pointer machine model, not constant though. So what we do is that we put all these things together, and then we can also navigate in the try in mlog sigma n time. And now I used my time, I can see. Oops, there's a little error here again. So overall, I showed you a compressed representation of tries using n divided by log sigma in space. And I showed you how top tree compression works, which I think is a very nice transformation of the trees. And then I showed you part of what it takes to get these optimal bounds here. And we have matching lower bounds. So this is actually optimum bounds in the pointer machine model for navigating in a tree using linear space. So that's it. Questions?
Thank you very much for your lecture. Yes, questions? There is one. Please come ahead.
Okay, coming from the very back. Thank you for the very nice talk. So you showed us that the compressed representation here is n divided by log n. Then afterwards, like after you do that, if I understand correct, the idea here is basically that you have the subtree, the DAG representation, and the internal, internal patterns at the same time, which you compress. So this is basically why you win so much.
Yes, it's because the DAG compression can basically alone, it can only take full subtrees that are equal, right? And now we can also find some internal thing. Yes.
Perfect. So if you take only that, so we know that basically on average it's something like n divided by square root log n. So kind of like we win another square root log n, kind of if we use internal only. Is that internal? Is there something as well? Has this internal by itself only analyzed as well, or is it like is it always combined? Is it always the subtree compression and the internal pattern compression?
It's both. Yeah.
Okay, so and my question actually, because I would just want to clarify that I was interested in just the DAC compression as well, and I looked like at the reverse question, like not if you take them and then compress them, but how many of a fixed compressed size exist. And do you know anything about that for these questions here for the top tree compression as well? It's kind of like
so if you want to take a DAC and then compress that, is
no,
that
kind of like I have how many, if I say it's the compressed size is the number of nodes it has then afterwards, after the compression, and kind of like how many of these objects are there? Because if you compress something, it could be you compress a lot or you compress nothing basically. And like I was interested in like the reverse question as well. It's just like this is really nice that I see these applications and all these or methods and things you can do with them. I was just wondering if you know something about a counting problem, a reverse counting problem.
So I'm not actually. So can you say again? So what is that you want to? I'm getting a bit confused about exactly what it is.
Yeah, sorry.
That you want to know.
Sorry. Yeah, exactly. So basically, if you compress, then basically you could basically say you have n nodes, then the compressed version could have the same number of nodes, basically, if I'm not mistaken, if nothing can be compressed, or it could be very small, like
yes.
So you have a range. You have a range. You compress in tree, something like log n and basically.
Actually, I mean, if the tree is large enough, then the top tree compression will be between n divided by log n and log n. Always.
Exactly. And I would like just to know if there are some results on kind of like as well, like with this top tree representation, how many have fixed compressed size?
No, I don't think so.
I mean,
but one thing I would like to say is so compared to when you talk in general, like when you talk about the SOCSIN data structures that my chief is going to talk about on Friday, they basically always use n divided by log space, right?
Okay.
Whereas this type of compression could be much smaller, so that's one of the differences. But I don't know the answer to the question you asked.
Okay, no. Thank you very much.
So thank you. Are there questions maybe from our friends that are online?
Conrado and Sebastian.
Okay, Conrado, please unmute.
No, I had a question before, but I made it.
You had your hand up earlier, Conrado, or was it up?
Conrado, we cannot hear you well.
I made my question during the lecture, so I'm sorry. Maybe I left this raised hand. Sorry. Thank you.
Okay. No problem. Other questions from the Sebastian?
Yeah, I have a question. You showed a few operations that you can also do on the pointer machine. But I know you worked on top tree compression with many more operations. Do you think are there roadblocks for other operations, or can you like generalize the algorithms you've shown to other operations on the pointer machine?
That's a good question. I haven't thought about other things you could do, but I think with the top trees and the top DAG, there seems to, I mean, all this overlap seems that if you want to compute things also like bottom up, for example, right? Stuff like that should be doable in here, but that's of course not a data structure question. Maybe lowest common ancestor could be interesting.
Yeah.
But I don't have a roadmap for exactly what you can do and can't do, but that's a good question.
If I may have a second question that probably you don't know, but this is interesting for this community, I think. Is something known about the expected size of top trees for certain distributions of trees?
No, but that would be very interesting actually, if you could show something for that. Yes, I would be very interested to see that. I'm pretty sure nothing is known for that. No.
I also
my-
think this little known, yeah.
So you have shown that it's the upper bound is n over log n, but
Yes.
is it typical, or if you just take a random compression, or what do you expect? So from your experience, that it's more close to n log n, or maybe smaller typically?
It depends a lot on kind of the how the tree looks, right? The more part-like it is, the more the happier somehow the top tree compression is. So it compresses parts really well, and so if it's like not very bushy, if you could say that,
Okay.
then it should compress better if there's longer parts that you can compress.
Okay.
That's one of the things, at least.
Okay. So there is one further question in the audience.
It's not actually a question, it's a comment on it. So the classical compression, they just merge something with the thing.
Could you come?
Yeah, I can come over.
Sorry, so the microphone is in the front, so people have to come in front.
So for the classical compression, we just merge subtrees that are identical, which is basically what you showed right at the beginning, the most simplistic case. I know that there are results for other random tree models, I don't know if there is anything for tries. For uniformly random binary trees, for example, or even for simply generated trees, on average, you get n over square root log n. Whereas for flatter trees, like binary search trees, you get n over log n. So that is known. For tries, I'm not sure, but
no, and that's just for DAG compression, right? So that's for
that's just for the simplest case, yeah.
Yes, yeah.
What you are doing with your compression is, of course, a lot more sophisticated. So
yeah, it would be fun to see if you could, yeah. I mean,
yeah.
So it's interesting research for us. Okay. So then I think these were all the questions that we have now. So so thank you very much again for your nice lecture, and